Hello everyone, today we will be learning about log laws. So log laws will be explored in throughout pre-IB 2, so that will be in grade 10. So this will be an important lesson if you guys are an IB program. Okay, so first of all, what do I mean by a log? So let's say we have an equation, log base x let's say y right here equals z. So what does this really mean? Because there may not be a clear relationship between x, y, z. So we want a clear relationship between x, y, and z. Well, this basically means that raising x to the power of z equals y. So if this equation is true, this equation is also true. I'm going to put this in exponential form. X to the z equals y. And you'll realize that in contest problems or test problems, right, you'll often it'll often be helpful to switch between logarithmic form and exponential form. So you could use context to determine which of these forms is more useful. And also, this arrow right here means that this equation implies this, while this equation implies this. So what I mean right here is that if this equation is true, then this equation is also true. And if this equation is true, then this equation is also true. So as an example, let's say I want to find the value of log base 2 of 64. What does this equal? Well, the value of this, I first have to ask myself, to what power of 2 should I raise it in order to get 64? Well, 64 equals 2 to the power of 6. Therefore, 2 to the 6 equals 64. Therefore, this will equal 6. Yes, that would be the value of this. So this is how you find values of logarithms. Okay, so after an introduction of logarithms, we will now be getting into log laws. Okay, so there are names to these logarithm laws. First of all, we will be taking a look at product rule. And we will be trying to prove that product rule is true. Okay, so how do I do this? Well, first I can introduce a variable. Let's say m, right? So let's say log base b of a equals m, and okay, this may be a little too to the right. I can move it over a little bit. Okay, let's say log base b of a equals m, and log base b of c equals n. Well, because these are true, from our introduction, we also know something else that's true. We will like to write this in exponential form. And this is another example where switching between logarithmic form and exponential form could be very beneficial. And in this case, writing everything in exponential form is very helpful for us, as we will see. So this implies that b to the power of n equals a. And this also implies that b to the n equals c. Now, if this equals m and this equals n, in order for these two sides to both be equal, this must equal n plus n. Therefore, we want to prove, what do we want to prove? We want to prove that our right side, which is log base b of a times c, equals n plus n. And again, we can write this in exponential form. If this is true, then we know another equation that must be also true, which is b to the power of n plus n equals ac. So we have two givens, right? So we are given that b to the power n equals a. We are also given b to the power n equals c. And we want to prove that b to the power n plus n equals ac. And also, you realize that when you're doing proof problems like these, it's helpful to write down your givens, what conditions you are given, and also the statement you want to prove. Okay, but this is true, right? Because, first of all, we have this equation, right? They're both true. Now, when we multiply b to the power of n, okay, let's say this is our proof. If we do b to the power n times b to the power n, if we multiply these two equations together, we get this, right? So this is true because these equations are true. Afterwards, we can use exponent law. Because these are the same basis, we can add the exponents together. So we get b to the power of n plus n equals ac. And this is what we want to prove. This is true as desired. Okay, so we are done. So this is product rule. Now this is called quotient rule. This is called exponent rule, and this is called chain rule. Now all of these are like the same flavors, right? You can set, so in this case, like it's pretty similar, right? You can set log base b to a equals m, and log base b of c to n. And afterwards, you can convert to exponent form, and it follows the same thing. And this one is similar as well. You can set log base b of a to a variable of your choice, and then it's pretty similar after that. And this one as well is pretty similar. So you can try them out as an exercise. So the last one. Last one, we'll be using, so you know how in algebraic equations, you have an equation, two sides are equal, and you do the same thing to both sides, while the equation is still equal. The same case it is for doing logs. When you take the log with the same basis to both sides, well, the equation is still true. So what do I mean by that? So let's say you have this true equation. Now I'm gonna do log base a both sides. Log base both sides, right? Now we have this. Well, because this equation is true, and I took the log base a of both sides, well, this is also true. And to see this more clearly, well, if I put brackets around this, right? Let's say. And now it's more clear because these two are equal, therefore you must raise a to the same power in order to get what's inside here. Now, this, taking the logarithm of both sides when the logarithm is in the exponent, is useful for many problems because then we can use our exponent rule and bring that logarithm down. Because we do not really like logarithms and exponents because they're hard to work with. However, if we bring the logarithm down, it will be easier to work with. So, in this case, we can apply exponent rule, and we get log base b of a times log base a of b equals log base a of a. And afterwards, we can apply our chain rule right here. So what does this become? Well, after applying our chain rule, then we just have to substitute some variables. And after substituting variables, by chain rule, you get log base b of b equals log base a of a. So this side equals 1 because in order to get b, well, b to the power 1 equals b. So therefore this side is 1. This side is also 1 because a to the power 1 equals 1. So at the end, we get 1 equals 1. And this is true. Yeah, and we are done. So this is why this is also true. Well, if you think about as well, so let's say log base b is a, so this is the power you want to raise b or to get a. So yeah, you have that. Well, b raised to that power, right, to that same power, well, of course, it will equal a. So this, I guess, is another way you can logically think about this. However, if this is like not clear to you, well, there's this one, taking the logarithms of both sides. Okay, now I guess we can look at a few problems that puts these logarithm laws to use. Okay, so let's say we have a problem x to the log x equals x cubed over 100. Okay, let's say we have this. Now, what's difficult about this problem is that the logarithm is an exponent, and we can't really do much about that logarithm in the exponent. However, as we have discussed before, one way to solve this problem is to take the logarithm of both sides. And this is what we can do here. And also, if there isn't any number below, and that is implied log base 10, right? So basically, log base x with nothing underneath equals log base 10. The base will equal 10, so b equals 10. Yeah. Also, in some contexts, you might see this ln of x. So what does this mean? Well, this basically implies that b equals e. This equals this. And e will equal 2.71828 and so on. So this is a famous constant in mathematics. Yeah, so this is another thing right here. Okay, but now we're going to take the logarithm of both sides. Okay, and now what we see happening is that the log x, it comes out of the exponent and comes in front using our exponent rule right here. So this will become log x squared, because this will become log x times log x, and that will become log x squared. While this side, well, we can use quotient rule, because we see a division right here, and this will equal log base x cubed minus log base 100. And this one, we can use our exponent rule again. We can bring the 3 out in front. While log base 100, well, to what power do I need to raise 10 in order to get 100? Well, 100 equals 10 to the power 2. Therefore, log 100 equals 2. Okay, so we continue. And now we move everything over. One thing right here, we also recognize this is actually a quadratic, except the variable is not x, it's actually log x. And if this is not clear to you, well, you can try substituting log x with any variable of your choice. Let's say we can substitute with y, and then you'll see that you'll get y squared minus 3y plus 2 equals 0. And this is a factorable quadratic. However, right here, let's first move everything to one side. And then after that, we factor. And we solve for log x, right? So log x equals 1. we also have log x equals 2. Yes. However, we are not done. Remember that, yeah, we are actually solving for x. We're not solving for log x. However, this is not really complicated because remember in our introduction, like if the logarithmic form is true, well, we have an equivalent exponential form. And so in this case, x equals 10 to the power of 1, which is 10. And from our second value of log x, we have x equals 10 squared. So so x also equals 100. And these are our solutions. And also, it is always a good idea to check back. If you plug everything in, you should get that these two sides are equal. Another important type of problems is solving logarithmic equations that have restrictions, so restrictive values. Because, well, this will be a common type of problem throughout your second year of pre-IB. And what I mean by this is that sometimes when you solve logarithmic equations, you get a bunch of values of x, right? But not all values of these values of x will actually satisfy the logarithmic equation because logarithms, they have a restrictive domain. Okay, so what is an example? So we have log base 10. So we have log x minus 1 plus log x plus 1. Let's say equals 0. Right? And we have restrictions actually right here. We require this to be positive because if we think about our exponential form, if we take any, so if we have 10 right here, right? If we take 10 to the any power, our result will always be greater than 0. And this can be seen if you graph like 10 to the x, you'll see that it'll kind of go like this, right? It never goes below 0. So therefore, x minus 1 cannot go below 0 as well, right? So therefore, x minus 1, already here. So our restrictions right here. So we have x minus 1 is greater than 0. We also have x plus 1 is greater than 0. So this will give you x is greater than 1. This right here will give you x is greater than negative 1. If you combine these two together, you'll get that x is greater than negative 1. So this is important because as we solve this equation, we might actually get a value of x below negative 1. And this value of x will not satisfy this equation because if we substitute that value of x right here, you'll see that this is actually not defined. So we can't have that. However, everything else, we continue as normal. We find a value of x, and then afterwards, we check whether they actually satisfy the equation. So we have this, and we can apply our product rule. So we have log base log base 10. We have x minus 1 times x plus 1 right here is equals 0. Yeah, writing this in exponential form, we see that this once again helps us. We can expand this using difference of squares. X squared minus 1 equals, we see that this will equal 1 because 10 to 0 equals 1. After rearranging everything, you get that x equals positive negative square root of 2. Now we check our restrictions right here. So x equals root 2 satisfies this inequality. However, x equals negative 2, negative 2 square root of 2 is actually less than negative 1. So this will not satisfy this equation right here. Because if we substitute x equals negative square root of 2 into into any of these, right? Well, both of these log aren't defined. Therefore, we have to discard one of these values. We have to discard this one, so there is actually only one solution right here. So, in conclusion, when you're solving log equations, always be careful of restrictions, and this will help you lose many unnecessary points on your IB exams. Thank you very much for watching.